First of all, when we talk about intermolecular forces, you need to understand that we are not going to talk about ionic compounds or giant covalent compounds or metallic compounds. It's only for the discrete molecules. What does that mean? Small molecules. So we are going to see the different intermolecular forces. The intermolecular forces are which are the forces of attraction of different compounds when they are molecular. For example, how water and water molecules act with each other, how ammonia and ammonia compounds work with each other, or the molecules, how hydrogen and hydrogen act with each other, okay? The different intermolecular forces depend on the shape and the polarity of the molecule. So we are going to see, basically it's not only that, there are some other things, but we are going to begin with the simplest one. And the simplest one is the dipole-dipole interaction. Okay? That it's going to be present when you have two molecules that are polar. In other words, let's pretend that I have here hydrogen chloride and I have here hydrogen chloride. Yes? We know that this molecule is what? Polar or non-polar? It's polar. So the electrons are going to be more localized over the chlorine, yes? And on the other side, we are going to have the hydrogen that is going to be kind of alone because the electrons pass more time over the chlorine than over the hydrogen. Is that okay? So these molecules are going to be attracted to each other, what we call dipole-dipole force. Yes? So the only thing that you need to know is that when we have a polar molecule, two polar molecules, we are going to have dipole-dipole bonds. And we normally represent the intermolecular forces with dashes. It's not one dash. This one is going to be the covalent bond, okay? Now, if I have hydrogen sulfide, for example, I'm going to put it here, hydrogen sulfide, hydrogen, hydrogen, sulfur, and hydrogen, hydrogen, sulfur. Yes? So this is again what kind of molecule? It's polar because it has the molecule itself is not linear. Yes? So we have the part that is going to be kind of negative over the sulfur because it's more electronegative than the hydrogen. And again, the hydrogen is going to be more bluish because it's lacking electrons. So they are going to attract each other like if they were magnets. The same thing. Okay? So the bigger the attraction, the bigger is going to be the melting and boiling points. Why is that? Because when we melt something, we are not breaking the bonds inside the molecule. We are breaking the intermolecular forces to separate them so they can escape as a gas. Do you understand? Good. Because in the dipole-dipole, there is a special dipole-dipole that we know that is called hydrogen bond. And why hydrogen bond? Of course, because hydrogen is involved. So which are the conditions? First one, the molecule needs to have hydrogen. If it doesn't have hydrogen, of course, there is no hydrogen bond. Okay? The second property has to be, hydrogen has to be attached to only 3 elements. Okay? To oxygen, to nitrogen, or to fluorine. Why is that? Actually, these are not molecules, these are atoms. To oxygen, to nitrogen, or fluorine. Why is that? Because those are the most electronegative elements ever. How do you know that? Look at the periodic table and you're going to see that they are going to be the 3 that are at the top right of the periodic table. Yes? And the third condition is going to be that the atom, in this case oxygen, nitrogen, or fluorine, have to have lone pairs in it. In other words, if there are no lone pairs, if all the, let's say that the hydrogen is attached to the nitrogen, but the nitrogen is using all the lone pairs that it should have with another element, there is no hydrogen bond. Why is that? Because the hydrogen bond occurs between the lone pairs in one molecule and the hydrogen in another molecule. Yes? So let's analyze the easiest one. You have you have water, or the hydrogen fluoride. Yes? And this molecule is going to be polar. Yes? And you may think that it's going to form a dipole-dipole bond. But the fluorine has pair of electrons that are not used with the hydrogen. That makes a intermolecular force between those, but it's much stronger than the dipole-dipole. The result of this is the hydrogen fluoride, the ammonia, and the water have very, very high melting and boiling points, comparing that with the elements that form the same molecules in the same groups. In other words, to break this bond, we need more force than to break this bond. Yes? Now, yes? Nothing? Okay. Now, let's do another example. Let's say water. H, O, and then H, O. Ah, yeah, it is like that. Oh. I'm getting tired. This and this. So we are going to have the hydrogen bond between these pair of electrons and these hydrogens. So it's going to be like that. Yes? That results in more attraction between the molecules because these bonds are bigger than a regular dipole-dipole. That means that we need more energy to break those bonds and melt water or melt hydrogen fluoride or melt ammonia or boiling. Huh?
Can water be melted? Can you melt water?
Yes, from ice to water. Yes. Okay. The hydrogen bonds are also responsible for the structure of the ice that holds the atoms and the molecules of water a little bit further away, and they are going to float in water because the molecules are going to be a little bit farther away than in the liquid form. Okay? The last one is the van der Waals forces